and the axion coupling constant. This is that GA gamma gamma value on the y-axis. The QCD axion lies in this yellow band here, and there have been quite a few searches for axions, but only one search for axion dark matter, and that is from the very cleverly named axion dark matter experiment. And they have done a fantastic job of measuring all the way down to the QCD axion regime, but they actually can only measure in a very narrow mass window, and that is because of a limitation of their axion detection technique. Abracadabra seeks to be sensitive to axions in this range down here. So to zoom in on that region, so this is where ADMX was. There are two parts of this parameter space that are worth talking about. There is this region here, which we call the axion-like particle parameter space. And discovery in this region would be indicative of a particle that is in every way like an axion, hence the name axion-like particle, but just does not solve the strong CP problem. So particles in this area are predicted by a lot of beyond the standard model theories. So a discovery in this range would actually be very interesting for beyond the standard model physics. And then the second region, of course, is this QCD axion region. This is the particle that both explains the dark matter and solves the strong CP problem. So where is Abra 10 centimeters? So this is the ultimate sensitivity that Abra 10 centimeters could achieve if we could hit our noise floor. Because of some earlier measurements, we don't think we'll be able to hit our noise floor. So we'll probably run with this slightly higher noise level, and that's okay for now. But what's really interesting to point out here is that we are still testing new parameter space. This is still unprobed regions of dark matter parameter space. And so what's sort of incredible about this to me is when I think about dark matter searches, I picture, you know, LZ and Super CDMS and Panda X, and these are ton scale experiments running deep underground with huge amounts of shielding. Abracadabra 10 centimeters is the size of a basketball, right? And it's running just in our lab. And so it's a very small tabletop almost experiment that is still sensitive to new regions of parameter space. And that really speaks to the power of this approach and just how wide open this parameter space really is. I should say that there are two modes that you can read this out. This is the broadband mode. There is also a resonant mode that you can read it out. If you're interested, we can talk about that later. So that is where we are now. What do we ultimately want to do with this? Well, ultimately, we'd like to build an experiment that we've called Abracadabra 75 centimeters. And we've called it 75 centimeters, of course, because it is, in fact, 3 meters by 2¼ meters. Here it is compared to Batman, who is actually 6'2", apparently. And Abra 75 would have a maximum field of between 1 to 5 Tesla. And one of the main goals of Abra 75 would actually be to develop that resonant readout. And so this is something that I'm particularly interested in. And if we'd be able to do that, we could actually be thermally noise limited to ideally around 100 millikelvin. And so this is something that requires a great amount of work, but something that I personally am very interested in doing. This is what Abra 75 centimeters would look like. I should say this Abra 10 centimeters is 1 month of data. Abra 75, this is 1 year of data. So with 1 year of data, we're cutting deep into the axion-like particle parameter space, and in the resonant readout mode, we're actually beginning to cut into the QCD axion regime. And so I should say that these resonant curves should be taken with a grain of salt. A more aggressive curve would actually go down another 2 orders of magnitude, but this really depends on how well you can build a resonator. So this is still very much to be seen. So to conclude, I think I've run a little bit over, but to conclude on the axion dark matter side, I hope I have convinced you that the axion is a viable solution to both the strong CP problem as well as the question of the dark matter density of the universe. And what I really didn't have time to get into is that actually there are quite a few axion dark matter searches that are currently experiencing a surge of new interest. This is a growing field, and there are quite a few experiments that are really being built on these sort of tabletop size. So the coming years will be a very exciting time for experimental searches for axion dark matter. So this is very well, exciting. So with that, I thank you for your attention. Sorry for running over.
I'll let you take the question.
Question?
Why Colloquium 130 over all the other double beta isotopes?
So let's see here. So to first order, the answer is that tellurium 130 has the high natural isotopic abundance. This is the isotopic abundance on the x-axis. Most of your neutrinoless double beta decay candidates have isotopic abundances around 10%. And so if you want to build a detector, you either sort of take a hit of 90% of your isotope is, or 90% of your material is not useful, or you enrich. And enriching is expensive. It increases the cost of your material by something like a factor of 1,000 or so. So tellurium is nice. It has, if you just pull up natural tellurium out of the ground, you wind up with about 33% of it is tellurium 130.
Can I follow up? Is this what Snow Plus is doing too? Are they doing the same isotope?
Yes. I don't know if they're enriching.
Maybe you could compare and contrast. I mean, they're low resolution, but Camla and Zen did so well, right?
Yes. So Snow Plus. Snow Plus is a large liquid scintillator detector. Let's see here. If I go back here, basically these are the 4 requirements that you have, but it is very difficult to and all of these together. A lot of these sort of trade off with one another. So the Snow Plus experiment is a large liquid scintillator detector. It is in the old SNOW experiment that's up in Sudbury. And what they have, what advantage they have is the large detector size. With liquid scintillator detectors, you can basically just keep dumping isotope into your detector, and you just keep increasing your mass by just pouring in more and more isotope until it's saturated and it starts precipitating on the bottom. But what they lose is low background. What they lose is the good energy resolution. So whereas Quarry has an energy resolution of around 0.2%. Their energy resolution is, I don't know this off the top of my head, but it's a couple percent. Yeah. And so what sort of becomes a problem for them is if you increase this by order of magnitude, this 2 neutrino signal begins leaking into your neutrinoless area. You can do anything you want about naturally occurring radioactive backgrounds. You can't get rid of this 2 neutrino signal because it's just the other decay channel. So that's a trade-off. Yeah.
Speaking of that 2 neutrino signal, do you have a plot of it just to show us how nice it looks in your instrument?
Let's see. That is a good question. The answer is, if you're expecting to see something like what you see out of Camland Zen or EXO, it doesn't look as nice. So this is what it looks like. This is from the Quarry 0 experiment in red, Quarry in blue. And the reason is that what EXO and liquid scintillator experiments can do is they can fiducialize. Right, so they basically take, the inner 10% of their detector, and they say that everything else is garbage. It's just shielding. Turns out that it's very expensive shielding, and so they can get rid of all of these gamma rays. We cannot do that, so we see quite a significant gamma background. So that's why you don't see that nice hump that you can see in EXO and Camland. But we will later this year come out with a 2 neutrino analysis, and you will see that a significant fraction of this is actually that 2 neutrino double beta decay. And it's really somewhere down here where the backgrounds start taking over.
Could you say something about the broader context of experiments that look at the hierarchy question of the mass hierarchy of normal versus inverted? I mean, there's another program of just trying to, decide which is the bit 0 or 1.
Right.
In terms of that, and what the time scale of that program looks like?
Okay, I don't have a great slide for this, but okay, so the issue of the mass hierarchy of the neutrinos. We know that the neutrinos, there are actually 3 mass states for the neutrinos. There is a small splitting between 2 of the masses and a large splitting between 2 of the masses. What we don't know is whether there is 2 light neutrinos, 2 neutrinos that are close to each other at the bottom, and then 1 heavy, or vice versa, 1 light at the bottom and 2 heavy. That's called the mass hierarchy. And so that's why there's sort of the inverted hierarchy up here and the normal hierarchy down here. So this is something that we would like to answer in the coming generation of experiments. Neutrinoless double beta decay is not a great way to get at this. And the reason is that neutrinoless double beta decay is really trying to answer the Majorana nature of the neutrino. So first of all, if neutrinos are not Majorana, we would have no sensitivity. We would just never see anything.
Yeah.
If you did make a discovery, you would actually need to back it up with multiple isotopes to rule it into this region. You would need to measure the neutrino mass scale, perhaps, because if it's, so neutrinoless double beta decay would just put a line on this plot. So if it's here and you didn't know the mass, it could be...
I can't see the pointer.
Sorry.
It's down. Maybe you should just use the
Okay.
There's
So-
a smaller one on the...
Yes, I was going to say, this seems
a bigger one.
a bit large. You would have to stand far away. Okay, this is a little bit better. Okay, if you measure the neutrinoless double beta decay rate, you would put a line here, and you wouldn't be able to tell if it was over here in, let's say, the normal hierarchy, or down here in the inverted hierarchy, right? And so to do that, to distinguish them, you would also have to measure the neutrino mass.
Well, what I was really asking about are the other kinds of experiments. I mean, it isn't like hyper K or things like that. Aren't they meant to? I mean, because the new 1, new 2 are the solar neutrino news, and the new 3 is the atmospheric neutrino.
Right.
So anyway, my impression, not being at all an expert in this area, is that there's a bunch of experiments that are going to try, or have been, in fact, already trying to understand this hierarchy, and I just wasn't clear on when they would have some sort of serious result.
So it depends. Let's see, I'm trying to remember if NOVA is sensitive to the hierarchy. So there's a currently running experiment called NOVA, and I know they're trying to measure delta CP. I can't remember if they're sensitive to the hierarchy. But ultimately, the experiments that really want to pin this down are hyper K. And hyper K is a super K. So if you know Super Kamiokande, it's a 50 kiloton water Cherenkov detector. It's 40 meters by 40 meters, and hyper K wants to be 20 times the size. So the time scale of that is long. I think the Japanese government is going forward with it. The other one that seeks to really pin it down is DUNE in the US. So this is DUNE LBN F, I believe is what it's called now. The time scale of that could be, once they start running, it could be as fast as a few years, or it could be as late as 2030 or 2035, something like that. So it depends a little bit on what the CP violating phase is. NOVA does have sensitivity to it, and so they have slight preferences for I think the normal hierarchy, but it will be probably another experiment that gets a 5 sigma measurement.
Yeah, these axions have electromagnetic interactions or effects. Is there nothing observable electromagnetically at the galactic scale? There's enormous amounts of these. if they form the dark matter?
Yes. So in terms of galactic, I would have to think about, but I can tell you that you would see other effects in terms of stellar lifetimes. For instance, this region here has been ruled out by supernova 1987A, and it was just, I don't remember exactly how that's done, but it's just if a supernova or star can lose energy through axions, that's a very efficient way to give off energy, and so you wouldn't be producing either neutrinos or the light that you would be producing. So they've ruled out that one. Up here is telescope experiments, and this, I believe, comes from looking at this is also a stellar lifetime, so this is rather than looking at supernova, this is how quickly stars burn off, deplete their fuel. Because axions would be a very efficient way to get rid of it. In terms of galactic things, I might have to look that up.
You mentioned when copper shield is tin. Is it
Yes.
pure tin? Because it has a phase transition at low temperature, making it powder.
Yes. So the tin. So normal tin has a superconducting transition around 3.5 Kelvin. I don't know the purity of the tin, but we have seen it undergo the superconducting.
I'm asking because the South Pole expedition, but Scott perished because of that problem with tin. The canisters were soldered with tin, and turned at low temperature turned into powder, and they lost their fuel.
Our tin has worked okay so far. I don't think we would be as in much trouble as they would, but
So when it gets cold, it grows dendrites and
Right. It
cause
turns
some
into
problems.
powder.
No, it doesn't, it's mostly fine, like, especially if there's some lead
Might be
out.
not very good.
yeah. So far our tin has been okay.
Two more than we should have.
So there's been lots of these simulations of what happens to the galaxies, assuming various dark matter models. As far as I know, all those models are sort of static pictures of dark matter. If it's the axion picture where I have these oscillations, do those simulations change, or not?
I don't believe so, and the reason is that even though the field is oscillating quickly, what matters is in those simulations is the energy density. And the energy density behaves like a matter, not a radiation. And this is, sort of it is in the classical sense heavy, because so the argument that everybody always says, if you take one axion out, the field looks still the same, right? So you can scatter off of it and it still looks the same. So once you get to the point of galaxy formation, I think no, not that I'm aware of.
I would interject that for very, very low masses, like 10 to the minus 20 eV, it can have an effect. But that's not on this
Yeah,
scale.
yeah.
What did this have in here?
For 10 to the minus 20, 10 to the minus 21 EV, it can have an effect. But not at least.
Yeah. Well, so at around 10 to the minus 15, you actually start running into limits from some really interesting limits from black holes, where you can actually form like gravitationally bound axion clouds around black holes that deplete them of their spin. And so we can actually probe very low mass through that way.
Very last question from Scott. You have a slide very similar to this one, but you have Abra projection
Yep.
limits. Yeah, those.
Yeah.
Can you just help us understand the shape of those limits on that plot? Like why they look, because actually, to me, it looks a lot like the dark matter curves that we all in the WIMP world
Sure.
draw, right?
Okay, so, let's see here. Yes, so this has to do with, okay, so you're talking specifically about the broadband one?
Sure, yeah.
Okay, so the broadband one, in principle, you just have better and better sensitivity as you go farther and farther to lower and lower mass.
Whereas that's lower
and-
frequency, right? The mass
Yes,
is frequency.
and this is just because, you know, if you imagine your oscillation is 1 year long, and you're sampling at a megahertz, right? You have a lot of points along that, right? So why does it turn up? Well, it turns up actually because of our squids. If you just, this is assuming the natural noise floor of our squids is flat, above between 10 and 50 hertz or so, and then at some point it turns up and 1 over F noise takes over. So that is why it curves up. There's
Okay,
nothing,
sure.
there's nothing sort of special about that curve up. Yeah, does that answer your question?
Yeah, yeah.
Okay, thank you, John.